in which I present our work on the time optimization of trajectories using zero-clamped cubic splines and the analytical gradients. So what is the motivation and goal of our work? Recently, we had to integrate a collaborative robot in a logistics facility. The robot's workspace was polluted by unknown objects, like randomly located boxes. For planning the robot's motion, we used a standard motion planning pipeline. Within that, a path planner computes collision-free waypoints that are then interpolated by a trajectory generator. A subsequent motion controller tracks the trajectory at 1 kHz. Our contribution is within the trajectory generation. Our work efficiently interpolates multiple configuration space waypoints Qi such that a smooth and fast trajectory results. We choose cubic splines for the interpolation because they are smooth by design and they provide an analytic description of the trajectory. The goal of our work is to interpolate waypoints in C-space with cubic splines such that the trajectory is zero-clamped. Zero-clamped means that both the velocities and accelerations can be set to zero at start and goal. This is not the case with cubic splines by default. Further, we want to exploit the actuator limits, that is to say, the maximum possible velocities and accelerations to obtain a fast robot motion. This is also not the case with cubic splines by default. Finally, we target an easy to implement approach with low computation time. So how did we achieve our goal? Our work builds upon the approach proposed by Lin et al. They solve the problem of zero-clamped cubic splines by introducing 2 virtual waypoints after the first and second last waypoint. They further exploit the actuator limits by formulating this optimization problem. The goal is to minimize the total trajectory duration t, which is a sum of the individual motion segment durations hi between the given waypoints. The constraints are that the given maximum actuator velocities and accelerations and jerks are not violated at any time. However, the solution algorithm for the optimization problem of Lin et al. Is involved and specifically designed for this problem. Our contribution is that we derive the analytical gradients for the optimization problem and that we exploit state-of-the-art optimization solvers to determine the duration of the motion segments hi. The given optimization problem and the derived analytic gradients are the input to a sequential quadratic programming solver that we use. I refer to our paper for the derivation of the analytic gradients. So what are the results? Of course, one could solve the given optimization problem also with numerically approximated gradients instead of the analytic gradients, for example, using forward or central differences. However, we show that the computation time increases significantly in this case. We further benchmarked our proposed trajectory generation approach with the 3 methods implemented in MoveIt. The computation time of our approach is longer than those of MoveIt, and also the trajectory duration is longest. However, in contrast to these approaches, ours can track the given trajectory accurately due to its smoothness. Further, our computed trajectory represents the actuator limits at any time. Here we see the position and velocity profile for 2 joints. The black lines show our approach. In the velocity profile, we see that the maximum possible velocity defined by the actuator is exploited in the motion segments. Thank you for your attention.